Okay, so here's a presentation on using the VSP2 to obtain data for relief sizing. This particular system we're going to look at is Epichlorohydrin hydrolysis with water. This presentation was given at the 2019 joint Dyers meeting in Ettlingen, Germany. So a list of topics that we'll cover. We'll discuss the chemistry of the hydrolysis of epichlorohydrin with water, and then we'll use the data to look at some case studies for event sizing to show how you would use the VSP data to perform relief sizing, and we'll perform the event sizing according to the ISO 4126-10 standard. So to begin, we have the mechanism of the hydrolysis of epichlorohydrin with water. This mechanism is found in the article by Gaka. The epichlorohydrin epoxide ring is opened by the proton. In this particular case, we were using nitric acid as our catalyst. The epoxide ring is opened and allowed to react with the additional water, and there it's hydrolyzed into what's often referred to as MCPD, or 3-chloro-1,2-propane-diol. This was assumed to be the only mechanism for this process, but in the article by Gaka, they actually found that there's two mechanisms for creating the MCPD. The water can actually react directly with the chlorine atom on the epichlorohydrin and generate this glycidol molecule. It only exists for a short period of time and ultimately reacts with the HCl byproduct from this reaction, winding up as MCPD as well. So over a long enough period of time, the epichlorohydrin all hydrolyzes with water and becomes MCPD. So in these particular experiments, we're going to be using epichlorohydrin and water. And in the first experiment, it's going to be catalyzed with nitric acid, and we'll be heating up to our process temperature to also drive the reaction. So the instrument that we'll be using to obtain the data is the VSP2. The VSP2 is a low thermal inertia apparatus, so that means that the heat capacity of the test cell is very low compared to the heat capacity of the sample. This means that when the sample is generating exothermic heat during the reaction, the heat will stay in the sample and heating it like it would in a large-scale vessel, as opposed to heating the test cell itself. We used a closed cell test cell. We measure the pressure inside the test cell using this line. And then there would be a secondary line connected for adding chemicals into the test cell. The temperature of the sample is measured directly, and then we're also measuring the temperature outside the test cell, and that's how the system keeps the test cell and the sample adiabatic. For a closed cell test, we're also measuring the pressure in the larger containment vessel. And then the system uses automated pressure balancing in order to prevent the pressure differential inside the test cell and outside the test cell from becoming too great. In order to get the low thermal inertia test cell, it's very lightweight, so it's not able to withstand high pressures. So we actually add nitrogen outside the test cell to keep the pressure differential low, keeping the test cell intact. The instrument can measure temperatures from as low as -70°C up to 1,000 degrees Celsius. And you can run open or closed cell tests depending on the system. A typical test cell is 120 mils. The test cell in this test is 110 mil test cell. And it uses magnetic stirring, so there's a stir bar in the bottom. And this all goes inside of a 4-liter high pressure containment system. So here's our recipe. We loaded deionized water and nitric acid into the test cell, and then the test cell and the the sample was heated to 80 degrees Celsius. And then we actually pressurized the test cell to an atmosphere of nitrogen, so that when we begin our metered addition of epi, it's not vacuum pulled right into the test cell. So we pressurized the test cell with a bar of nitrogen, and then we connected the epichlorohydrin with a metering syringe, so that we could add the epichlorohydrin at a constant rate over a 10-minute period. So the epichlorohydrin was in a separate high pressure stainless steel syringe, and it was set up to be added over a 10-minute period. So this is a picture of the setup. So we have our VSP high pressure containment. Inside is the test cell with water and the nitric acid. The nitric acid and water have been heated to 80 degrees Celsius. The epichlorohydrin, which is at room temperature, is in this small stainless steel syringe connected to the test cell through this fill line. And then when we reached stable temperature and pressure, we would begin adding the epichlorohydrin over a 10-minute period. So this is where we heated the water and the nitric acid to our process temperature of 80 degrees C, and then we kept adiabatic to get stability of the temperature. And at this point is where we began the addition of the epichlorohydrin, and then this was metered in over 10 minutes, and you can see there is exothermic heat generated from the reaction, which heats the entire sample from 80 degrees up to about 136 degrees C. And so not only is it heating the water and nitric from 80 C to 136 C, but it's also heating the epi from room temperature up to 136 C. So when we stop the addition, you can see that the reaction is pretty much over. It's no longer generating heat, and the temperature just remains constant. It looks very much like it's a rate controlled addition. So with the catalyst and the temperature of the process, it's pretty much reacting at the rate that it's being added into the test cell, as opposed to typical standard Arrhenius kinetics. So after we stopped the addition and we saw that the temperature was not increasing, we turned off the heaters and allowed the system to cool. So here's a look at the pressure. So this is, again, we were heating up the water and nitric. Once we got the process temperature, before we started adding the epi, we added the nitrogen pressure up to 1 bar so we wouldn't have a vacuum in the test cell. And then you can see the pressure rise as the temperature rises inside the test cell. Here's our temperature rise rate. So this portion is due to the heating where we added heat to the water and nitric to get it to our process temperature of 80 degrees C. And then this additional temperature rise right here is due to the exothermic heat of the hydrolysis of the epi. So as the epi is being added, the exothermic reaction is heating the sample up to about 136 degrees C. So here's the pressure temperature plot. There's a little bit of a pad gas at the beginning, but we heated up the material, and then again, this is where we added the nitrogen to get it to 1 bar. So we're not quite under vacuum. And then this is the heating of the sample. This is the pressure change with temperature as the exothermic reaction is proceeding. And then here at the end, it looks like maybe at these higher temperatures, there may be a different reaction going on where some non-condensable gas is generated, kind of giving a sign that we could be at the early steps of some type of decomposition or secondary reaction with the product. But the heaters were turned off here and the system was allowed to cool. So again, we had a little bit of pad gas here, and we definitely added some nitrogen here, so you can correct for what's been added. So this is the corrected pressure versus temperature plot here. So you can see once it's been corrected, the pressure follows the vapor pressure of water very closely. So you can see that that's what's causing the change in pressure. Is the increase in temperature is increasing the vapor pressure of the water, and that's what could potentially overpressure our system. So now we move to the case study part. We'll use the data from the VSP test and perform a vent sizing evaluation for this reactor. So we have a 10 cubic meter reactor with an MAWP of 1.5 bar G. The rupture disc that we want to use will have a set pressure of 0.67 bar G, which is about 10 psig. So now that we have our conditions for our vessel, we can use the data from the test to perform a relief sizing calculation using Prevent software. So we could tell from the pressure versus temperature data that the system it's a vapor system. So that means that the pressure that's being generated is due purely to an increase in the vapor pressure. Even though we did see a little bit of possibly non-condensable gas generation at the higher temperature, the relief device would actually open and begin venting at a lower temperature where it's just the vapor pressure of water. So we would consider this a vapor system. I assumed a flow regime of homogeneous vessel venting. We entered the temperature pairs, so this would be the vapor pressure of the system. So you entered two temperature pairs, and then you put in the temperature rate pairs. In this particular case, we didn't have Arrhenius kinetics because the reaction was limited by the addition rate. So instead of putting in the two parameters on the slope to get the Arrhenius kinetics, I just entered, I picked the temperature rise rate that corresponds to the set pressure where the rupture disc would open, and then I just kept that constant. So even though we saw it decay over time or as temperature increased, it's conservative to assume that it's going to stay constant and not go down. So we're actually using, we're telling the system that the temperature rate is going to stay the same, even though we've seen it go down as we continue adding the epi. So then the Prevent software takes these inputs and goes ahead and calculates the relief size requirement. So we're allowed to go 104. We have 146% available of overpressure to work with to get to a peak venting pressure of 1.65 bar G, which is 10% over our MAWP. And this shows you what your flow rates are and calculates that you need a rupture disc with a diameter of 9.8 centimeters. Now this is the ideal vent diameter, so it doesn't take the frictional losses into account. So when you do choose the rupture disc to actually install, you need to look at the frictional losses through the pipe. The software will also show you for a given diameter of pipe what allowable equivalent length you can have. So let's say in this case you have 50 meters of equivalent length of pipe in your outlet. The 130 millimeter disc would not be large enough. So you would have to select a 150 millimeter rupture disc to install to protect this vessel from this scenario. Okay. So a second test was performed. This was pretty much the same as the first test. The recipe is the same ratio of water and epi, but we didn't use any catalyst. So I was just curious to see if at our process conditions, if this reaction would still occur without the catalyst there. So without the catalyst, I went ahead and just added the epichlorohydrin and water into the test cell at room temperature. And then I loaded that into the VSP and heated it up to our 80 degrees C process temperature. So there's no metered addition this time. Both the water and epi are already in the test cell. So I heated this up to 80 degrees C, and it actually did react at that temperature even without the catalyst there. It was much slower. The other reaction took a total of 10 minutes to occur. This took closer to 2 hours to react, so it would make sense without having the catalyst in there. The reaction would be slower, but it did proceed at this temperature. So if you had a scenario where the operator did not add the catalyst, this would be simulating that upset scenario. So there was a reaction. It ended up at pretty much a similar temperature of about. The temperature was a little bit higher because the epi was not being added cold at room temperature. It was actually heated up to 80 degrees C in this test. So it did get to a little bit higher temperature, but actually epi has a very low heat capacity in comparison to water, so the peak temperature was relatively the same as in the first test. Now in this case, instead of allowing it to cool, because I noticed some reactivity at the end of the other test, I wanted to search and see if there were any other reactions to be concerned about. So I began a heat weight search routine. So we heated up to, I believe this is 140, and then 145. Ultimately, when we heated to 150, we did see another reaction occur, and you can see that reaction take off. I actually turned off the heaters to try and end this test when we were only at about 230 degrees Celsius, and I believe about 500 psi. But this reaction is so exothermic that even without the heaters keeping it adiabatic, it continued to react, and the temperature continued to increase and the pressure continued to increase. So you can see I shut off the pressure was about here when I shut off the test, and yet still managed to jump up pretty quickly to about 113 bar. So definitely very, very exciting. So again, you can see here, this is the heating up of the material where we actually added the heat. This would be the reaction of the hydrolysis of the epi. So you can see it's more of the Arrhenius kinetics that we're used to because the material is already in there. It's not mass transfer limited, so you have your Arrhenius kinetics here. And then the reaction of the hydrolysis is pretty much complete at about 135 or 140 C. And then we heated this up ultimately to 150, and then you can see the secondary reaction clearly occur. Again, the heaters were turned off at about 230 degrees C, but you can still see the temperature continued to increase. So it's a very energetic exothermic reaction here as well. So that's certainly something to consider in the relief system design. For the purpose of this case study, to keep it simple and fit in the allotted time, we're just going to focus on the vent sizing for this hydrolysis reaction. But it is important to take this into account when in your overall relief system design, because when you vent here, you could be transferring this material to another vessel. So you really need to know the flow regime to know if is it going to be venting mostly vapor, leaving this liquid behind. So now you potentially have this other reaction to deal with in your reactor. Is it truly homogeneous flow and it's going to vent over to like a catch tank, and now you potentially have to worry about this reaction occurring in your catch tank. So it's really important to make sure that you understand any other potential reactivity that could occur and understand the flow regime, so you know which vessel it could be located in and where you may need to deal with this reaction. But for the purpose of this presentation, we're just going to focus on the vent sizing for this hydrolysis reaction here. So again, we had a little bit of a pad gas, but not very much here. You can still see it mostly essentially follows the vapor pressure of water. And then at the 150C, where we saw that secondary reaction occur, it does look like it probably generates some non-condensable gas, and then continues heating up here as well. And you can see the final pressure is much different than the initial pressure, which would also be an indication that some non-condensable gas was formed. And you can quantify how much was formed just by looking at the initial and final pressures. You know your volume in your test cell, and you just use the temperature, the same temperature, to calculate moles of gas generated. So we take the data from the test, use the prevent software. Again, it's a vapor system. I assumed a homogeneous flow regime. Enter in the temperature pairs of the data, temperature pressure pairs of the data. And in this case, we do have the Arrhenius kinetics, so I did use the actual temperature rise rate at these two corresponding temperatures, so that an activation energy is then calculated. And so using the set pressure and the activation energy and the temperature and pressure rate pairs, the actual temperature rise rate at the relief conditions is predicted to be 1.45 degrees C per minute. So then the vent size was calculated according to the ISO 4126-10 standard. And it says here we need a relief device with a diameter of 6.129 centimeters. Again, that's an ideal size, so before we actually select our rupture disc, we need to look at equivalent length. Again, let's say we have 50 meters of equivalent length. So we would have to come down to this third option, and then we would need a rupture disc with a diameter of 100 millimeters. So, any questions?
Is the Prevent software a product of Fauske Associates, or?
Yes, the Prevent software is a Fauske product. It's a commercial product available for sale. So.
And it has many applications, so this is just one of them, or is it designed specifically?
Yeah, it's mostly designed for looking at relief sizing of reactive systems. So whether it be vapor systems, gaseous systems, or hybrid systems, it also has the functionality for looking at all vapor gas flow using the Fauske simple methods, as well as looking at two-phase flow and the Leon omega method and the ISO 4126-10 method.
So that has a lot of applications for nuclear and industrial, chemical processing, all different areas.
Well, it can be used for all other areas. So something like nuclear, where it's probably not chemical reaction, let's say you're looking at a steam relief device. There is also a module in there for, say, like fire heating. So that's a non-reactive fire heating module. So you can just look at essentially constant heat input and perform a relief sizing calculation. There's also a module for deflagration. So if you're doing deflagration vent sizing, the software has the capability to calculate the relief device for that as well.
And then the Dyers technology, what role does the development of that bench scale, or the role of Dyers in general, play in how?
Yeah, so when Dyers was originally started back in the early 80s, first they thought all they needed to do was come up with a methodology for the relief sizing itself, but they found very quickly that there really wasn't a good calorimeter for obtaining the data necessary for relief sizing. Instruments like the ARC were available, but because of the high thermal inertia, it was found to be very difficult to accurately determine the kinetics and perform modeling to do the relief system sizing. So it was very desirable to be able to measure the reaction in a low thermal inertia apparatus, so that you wouldn't have to be an expert in the kinetics of your reaction, because a lot of times these reactions are maybe side reactions or unintended reactions due to runaways. So it's very labor intensive to get a very solid understanding of the kinetics of the reaction. So if you have a lot of different systems you're looking at, it could be cost prohibitive to really have a fundamental understanding of the kinetics of every reaction that could lead to relief sizing. So to simplify that, it was found that a low thermal inertia apparatus was necessary to obtain the data for relief sizing. So what was originally developed was called the Dyers bench scale apparatus, and this was developed as part of the Dyers research program. Ultimately, after the program completed, Fauske commercialized the Dyers bench scale apparatus as the vent sizing package, or VSP, and then that was later upgraded to the VSP2. So it's a very important instrument for obtaining the data for relief sizing.
Excellent. It's used in schools as well, right? Universities.
Yes, there are a number of universities that have either the VSP2 or the ARSST. Both calorimeters are manufactured by Fauske. They're both low thermal inertia calorimeters. So they operate differently and have different capabilities, but both are in essence low thermal inertia calorimeters, and the data can be used to perform relief sizing.
Great. Thank you very much.
Thank you.